Hello everybody! Welcome to our video solution to problem 1 from quiz 3. This is from fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we have our old friend Clever Carl back, and he is trying to make a flashcard for our Basics of Functions standard. So that standard is all about defining and maybe even applying the basics of functions like domain, codomain, range, injective, surjective, and bijective. So what does Carl write down on his flashcard? So he says, if f is a function from a set A to a set B. Hey, that actually sounds pretty legit, right? We can do that. So why don't we just maybe try to write down maybe in some symbols or some pictures as we go through this, see what Carl is talking about. So f is a function from A to B, okay? From a set A to a set B. If we were drawing a picture, we might draw something like A being over here, B being over there, F goes there. Maybe we have some dots in A, right, representing elements, some other dots in B. Don't have to be necessarily the same number of them, and right, and so dots go to dots. Okay, maybe that's what it looks like. Or maybe we even have like maybe some sort of repetitions or something. One thing we don't have, right, because this is a function, is we don't have two arrows coming out of the same dot. That's never allowed. All right, well, let's keep going with what Carl wrote, right? The first part, that seems pretty legit. He says, if f is a function from a set A to a set B, then A is the domain. Yeah, this guy right here we call the domain. Oh my goodness, Carl's on a roll. Okay, then B is the range. And here we have our first issue. So, when we first learn about functions, we very often are taught about domain and range, and so we kind of get into the habit of just thinking, oh yeah, right? You go from the domain to the range. And there's a sense in which that is true, but there's also the more meaningful sense where it's false. So, if we write down a precise definition of a function, then a function is a subset of the Cartesian product of two sets, satisfying some extra condition. We'll talk about that extra condition in a second. But first, that's the very first thing, is f needs to be a subset of a Cartesian product of sets. When we say f is a function from a set A to a set B, we are specifying what those two sets are. The set on the left, the set A, goes on the left in the Cartesian product. To a set B, okay, that's on the right, that goes on the right of the Cartesian product. And we call, again, this first set the domain, but this second set here is called the codomain. All right, now how is that different then from the range? Well, this gets back to the definition of a function. So not only is it a subset of the Cartesian product, but it has a certain property. Satisfying, okay, what condition? For all A and A, there exists a unique, okay, this is very important, a unique B and B such that the pair A comma B is an element of F. Okay, now for functions, you're not used to writing it this way, right? We're used to writing it as f of A equals little b. Okay, this means the same thing. Okay, so the point is you give me an element from the domain, there is a unique element of the codomain that goes into this second position, right? Allows us to say f of A equals b. This is what I said earlier, where we can't have, right, a second arrow coming out of one point in the domain. That's not allowed, right? This is a no-no. Okay, so what this says, though, is that every element of A has to have what we call an image. Okay, so in this picture here, this B is the F image of little a. So everything has to have an image. But note, like even in this picture, I have arrows coming out of all my dots, but there are some dots, like that dot there, and even this dot there, they aren't the image of anything. And that's okay. We're allowed to do that. right? The definition doesn't require that every element of B have what we would call a preimage. Okay, so this little a here is the F preimage of little b. So we don't require, right, that every element of B has a preimage. But some elements do. And those elements that do have a preimage, those are what we call the range of B. So the elements of B that have an F preimage, or equivalently are an F image. Okay, if you have a preimage, then you are the image of that element. If you have a preimage, then if you are the image, then okay, whatever you're the image of, that's your preimage. All right? So the elements of B that have a preimage or are an F image, all right, or we should say the set of elements of B that have a preimage is the range of the function f. So what is happening here is he has taken B, called it the range, when of course it should be the codomain, and then he said, and f of a. Now what is f of a? Well, f of a is just actually another way of writing the image of f, or the range of f. So f of a, this is just equal to all things of the form f of little a, as a runs through every element. Right? These are all of the images, right? The set of all F images. This is also equal to the range of F. And this is a subset of B, right? Every image, right? The F image, right? This has got to be some element of B. All right? So what he's done actually here is he has swapped codomain and range. So these need to be swapped with each other. Okay, next, we say that f is injective if every element of A has at most one image. But you notice our definition of function says for all A and A, they have, well, actually a unique image. So this is somehow maybe confusing a little bit with the definition of function. In fact, injectivity starts from the codomain. It's what we call a right-to-left condition. So injectivity, f is injective, not if every element of A has at most one image. That's going from left to right. We say, oh, every element of A has an image. No, no, no. Instead, f is injective if every element of B, okay, so we're starting in the codomain, has at most one, well, we have to go backward, right? We're starting in the codomain, we have to go back to A, so it's going to be one F pre-image. All right, so this here, this image, that actually should be pre-image. All right, let's see what happened with surjectivity. F is surjective if every element of A has at least one image. And here Carl is going in the wrong direction again. He's treating this surjectivity as a left-to-right condition. But in fact, surjectivity is a right-to-left condition. So F is surjective. Right? We just write the same thing. Carl's almost right. He's just going in the wrong direction. F is surjective if every element of B has, well, now surjectivity means you have to have at least one preimage. All right? So injectivity, you're looking at the codomain and you cannot have two arrows going into one point. Ooh, look here. Two arrows going into one point. Yeah, that's no good, right? I got two purple arrows going into this one point. It means this function is not injective. And look, here's a dot that has no arrows going into it, right? It has no preimages. It's not surjective. Okay, so again, he gets this word wrong. Instead of it being image, it should be pre-image. Okay, finally, F is bijective if every element of A has exactly one image. Okay, well, this is the combination of injective and surjective, and if Carl had been right about injective and surjective, then we couldn't fault his definition here for bijective. But, again, he got those wrong. It's left to right in his world, but for us, we know it's a right to left condition, and so is bijective. In fact, bijective just means injective and surjective, but the combination of at most one preimage and at least one preimage is exactly one preimage. So F is bijective if every element of B has exactly one F preimage. Okay, and so once again, this word image is just not quite right. Okay, so if we can get Carl to make those changes, he's actually going to have a correct and useful flashcard. Hey, maybe you could make that up. All right, we'll see you next time.